Now, there is a special type of square matrix that has ones on its main diagonal and zeros elsewhere. For example, we can have this 1 0 0 0 1 0 0 0 1. We have first seen this whenever we're doing a reduced row echelon form. Now, we have ones on the main diagonal. When we say the main diagonal, those are the entries a sub 1 1, a sub 2 2, a sub 3 3, and so on, which forms like some sort of a diagonal line that divides somehow the matrices into two halves. If that square matrix has that main diagonal all ones and the rest are zeros, we call that the identity matrix of order n. In this case, this is of order 3 because it's a 3 by 3 matrix. In general, identity matrix of order n is of this format. When we know the order of the matrix is understood or given, I sub n can simply be denoted as I. As we will state in the next theorem, the matrix I sub n serves as the identity for matrix multiplication. If for matrix addition, we had the zero matrix, for matrix multiplication, it will be the identity matrix of order n. So, these are the following properties of the identity matrix. So, if A is a matrix of size m by n, then the following properties are true. If we multiply A to I sub n, I of order n, then it will be equal to A. So, for example, if we're going to have matrix A would be equal to 1, 2, 3, 4, 5, 6, then we would have I sub n. So in this case, A will be I sub 3, which would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. If we multiply this A to this I, if we multiply A by IN in that specific order, that would be 1, 2, 3, 4, 5, 6 multiplied to the identity matrix I sub 3. We're going to just have the same A, 1, 2, 3, 4, 5, 6. And we can verify that. 1 times 1 is 1. If we're going to verify this first entry, that will just be 1 times 1 plus 2 times 0 plus 3 times 0, which would be the operations that we would do to find the first entry in the multiplication. So here we have that first part of the property, or the first. So now we have the first property. Take note that A should be multiplied to IN in that order. If we are going to multiply the matrix in the second one, that should be in this order, I sub m times A. So in this case, if I will have I sub m, which is actually I sub 2, let's change the color. There we go. So we're going to have, let's say, I sub m. In this case, given this A is I sub 2, so if I will multiply my I sub 2 of 1, 0, 0, 1, so 1, 0, 0, 1 multiplied to matrix A of 1, 2, 3, 4, 5, 6. If you're going to look at it, the first entry will just be 1 times 1 plus 0 times 4. So therefore, we'll just arrive at 1. Continuing that, we will arrive at still the original matrix A. That is, if we multiply first the I sub m, which is the number of rows of A. So these are true, provided that we have to make sure that that identity matrix is consistent with the row or the column depending on where it is multiplied. Now, if A is a square matrix, say for example, I have, there you go, let's bring that down. So if it's a square matrix, for example, I have A is equal to 1, 2, 3, 4, then my I, which is just I sub n, in this case, I sub 2, I can have just the same 1, 2, 3, 4 multiplied to the identity matrix in this order would just be the same as multiplying first the identity matrix to the given, and I will just arrive at the same original matrix. That is the property of the identity matrix. So as an example, if we're going to multiply these two matrices, this matrices is actually 3 by 2, and this is our I sub 2, then automatically the answer would just be 3, negative 2, 4, 0, negative 1, 1. Similarly, here we have our I sub 3, and this is actually a 3 by 1 matrix, so the answer here would just simply be negative 2, 1, and 4. So again, if for matrix addition, its identity is the zero matrix O sub mn. For matrix multiplication, it is the identity matrix I sub n or I sub n, depending on where we multiply our identity matrix. Another feature of square matrices and matrix multiplication is that if for repeated multiplication of square matrices such as a squared and a cubed and so on, we use the same exponential notation with real numbers. So a raised to 1 is just a squared is matrix A times matrix A, and so on. Now, we also define a raised to 0, matrix A raised to 0 as I sub n, where A is a square matrix of order n. And because of this, we were able to establish the properties that matrix A raised to j times matrix A raised to k would just be the same as matrix A raised to j plus k, and matrix A raised to j raised to k would be equal to matrix A raised to jk, where jk are non-negative integers. This is your basic product rule and power rule in the rules of exponents of real numbers. So, if we would like to find a cube where a is equal to this matrix, a cube would simply be 2 times negative 1 times 3 times 0 times 2 times negative 1 times 3 times 0 times 2 times negative 1 times 3 times 0. So if we are to multiply it first, I'm using the associativity, I'll multiply this one first, and then we're going to have 1, negative 2, 6, negative 3, multiplied to 2, negative 1, 3, 0. Finally, we're going to have negative 4, negative 1, 3, and negative 6. The details of the multiplication are left to the viewers. So, those are other special properties of matrix multiplication, the identity matrix, and repeated multiplication of a square matrix.